Hello everyone. We were on an expedition to discover more about a grey wolf. So, stay tuned for more stories.
Good day, Doctor. We are from Group 3. The title of our paper is A Novel Clustering Method Using Enhanced Grey Wolf Optimizer and MapReduce. My name is Inchu and I will be presenting the introduction part. The article is talking about one of the clustering methods for clustering massive amount of data using Enhanced Grey Wolf Optimizer with a combination of MapReduce. The article discussed that the proposed clustering algorithms such as BAT algorithms, bee-colony, Grey Wolf optimizer unable to perform efficiently on large datasets due to processing limitations. Hence, this paper has proposed a new variant of clustering algorithm, that is, using eGWO along with distributed computing tool MapReduce to cluster massive datasets. So, what is GWO algorithm? The GWO is inspired by the social hierarchy and the hunting techniques of grey wolf. Basically, a pack of wolves are grouped into alpha, beta, delta, and omega. According to the algorithm, the best three positions are represented by alpha, beta, and delta wolf respectively. They are the main hunting agents because they have better knowledge on the location of prey. Meanwhile, omegas are the members following these three groups. The GWO is developed by imitating the hunting mechanism of grey wolf. Main steps for grey wolf hunting including encircling the prey, hunting, and attacking the prey. These steps have been converted into the following mathematical model. So, how GWO apply on the clustering? The algorithm starts with initializing a set of parameters such as the number of wolf population and the number of iteration. The first population is generated with random cluster centers in the boundaries. For each member of the population, according to the cluster centers, the fitness value is calculated. We will find the best three wolves with minimum SSE. Then, we will update the centroids of each individual using the position of the three leaders. After repositioning, we calculate again the fitness value of the new positions. According to the new positions, we will then replace the worst fit grey wolf with another best fit grey wolf. The process is iterating until the condition is satisfied, meaning the algorithm returning the best centroids with the minimum SSE. Thank you. Next, I will pass to my group mate. He will be presenting on the problem statement and the research objective. Thank you.
Hi, Doctor. My name is Kang and I'll be presenting about the problem statements and research objectives. There are three main problem statements in the research. Firstly, several data clustering algorithms has been developed to handle diverse data and application requirements. K-mean, which is one of the most common and simplest algorithms, was used to unravel the various clustering problems. However, the K-means algorithm's outputs are highly dependent on the initial cluster centroid, and thus has a significant risk of trapping in local optima. For the second problem statement, although various meta-heuristic-based clustering methods has been proposed, such as genetic algorithm, BAT algorithm, artificial bee colony-based method, and so on. These clustering algorithms fail to perform efficiently on large datasets in terms of memory space and time complexity. This is due to their sequential executions. Last problem statements. Based on the various research, Grey Wolf Optimizer, or commonly known as GWO, has outperformed existing meta-heuristic algorithms, namely particle swarm optimizations, evolution strategies, gravitational search algorithm, and so on. Although GWO has been widely used in numbers of applications in the last 3 years' time, GMO has a limitation of lack of population diversity, which results in slow convergence rate and risk of trapping in local optima. Next is the three main research objectives. Firstly, to propose a novel clustering method based on the new variants of GWO, which includes Levy flight steps and binomial crossover. Secondly, to include and parallelize the Enhanced Gray Wolf Optimizer, or commonly known as EGWO, into MapReduce architecture to have a more efficient clustering of large datasets. Lastly, to evaluate the performance of EGWO based on the clustering problem.
Good evening, Doctor. I'm Ishani Kumari. I'll explain the methodology part. The proposed method has three folds. First, introduction of enhanced Gray Wolf optimizer to improve the clustering quality. Second, parallelization of enhanced Gray Wolf optimizer using MapReduce to handle large datasets. Third, performance validation of proposed techniques. The success of GWO algorithm depends on equilibrium between exploration and exploitation. This algorithm has two limitations: slow convergence rate and risk of trapping into local optima. The intensification of the population around the current best solution inflates the generation of optimal solution. So, binomial crossover operator is used between the alpha wolf and ith gray wolf to update the position of ith wolf to inflate the attack to the prey. In GWO, position update of omega wolf is determined based on the position of alpha, beta and delta. This leads to immature convergence. So, Levy flight concept has introduced to update the position of each wolf. In order to cater the larger datasets, the EGWO were parallelized using MapReduce. Two phases of this are EGWO map and EGWO reduce. This diagram illustrates the architecture of the proposed method. First, the input data is split into small chunks and distributed among nodes. Then, each of this input split is converted into key value pairs by the record reader. Then, in map phase, these input key value pairs are processed with cluster centroid in parallel and find the centroid index of each point. In reduce phase, compute the corresponding fitness value of each gray wolf. Then alpha, beta, delta and population values are updated and the process is continued until stopping criteria is reached. 7 UCI datasets were used for testing. Intra-cluster distance and convergence behavior were used to validate the clustering performance. These are compared with 5 clustering algorithms. F measure was used to clustering quality measurement. These are compared with the 4 MapReduce based algorithms. Thank you. Kevin will continue from this point.
Hi, doctor. My name is Lim Kevin, and now I'm going to present on the result part. There were two folds of evaluation for the proposed method. Firstly, EGWO was validated for clustering, namely intra-cluster distance and convergence behavior. For clustering, comparison is made with k-means and 4 meta-heuristic algorithms, namely GSA, PSO, BA, and GWO. Secondly, MREGWO was vindicated against 4 state-of-the-art MapReduce-based clustering methods using F meshes, and these 4 methods comprise of parallel k-means, parallel k-PSO based on MapReduce, and MapReduce-based artificial bee colony optimization for large-scale data clustering, and lastly, dynamic frequency-based parallel k-bets algorithm. So for the last part, speed-up behavior of MREGWO was determined by increasing the number of nodes in each run. Next, section 1. This table shows two important results which are the best and mean fitness values of 6 different methods over 30 runs. Now, at the left-hand side with blue color denoting that there were 7 data sets being used, starting from iris to wine. The green color denoting that there were 5 considered methods starting from k-means to PSO, GSA, BA, and GWO. And lastly, at the right-hand side, you can see the EGWO was the proposed method, and the yellow color stars denoting that these were the best result obtained for the proposed method. whereas for the red color with a thunder sign denoting that these were the best result obtained, but not from the proposed method. After that, to validate the performance difference of proposed and tested methods, Wilkerson rank sum test was conducted at 5% level of significance. As you can see from the small box at the bottom, the p-value is less than 0.05 in all the datasets, and EGWOs was significantly different from considered methods except GSA for balanced dataset, which was shown by the red color box over there. Next, convergence behavior of EGWO and considered methods were applied on two datasets, namely wine and glass, to show improvement in exploration and exploitation trade-off. As you can see from the red color arrows over there, EGWO was having higher exploration at the early stage of iteration, then reduced to perform exploitation. The decline at the later stage will exploit the search space well to find optimal solution. Thus, EGWO was proved to have a good ability in exploration and exploitation. Also, Botsprot will be able to show the consistency of the clustering result. As you may observe, EGWO was having minimum degree of dispersion. Therefore, EGWO will be an effective alternative to perform clustering. Moving next, section 2. 4 large-scale synthetic datasets will be used by duplicating every record of original dataset by 10 to the power of 7 times. As you may observe, second table here shows the mean value of F measure and computation time for 4 large-scale synthetic datasets, and also every method on a cluster of 5 machines. Next, MREGWO outperformed all the other methods as shown by the yellow color box at the right-hand side. The computation time for K-means was less, but it had the least performance. Lastly, MREGWO was suitable for efficient clustering of large datasets. Moreover, speed-up performance of MREGWO was identified on 2 datasets, which were IRIS and CMC. As you may observe at the 2 charts at the center, when the number of machines increased in Hadoop cluster, the running time of MREGWO dropped gradually. With 5 machines cluster, proposed method achieved a speed-up measure of 4.6754 for dataset 1 and 4.3457 for dataset 2. Thus, proposed MREGWO fit well for large-scale datasets.
Thank you, Kevin. Hello again, Doctor. As I didn't get the chance to introduce myself earlier, allow me to do the honors. I am Anik, and I will be concluding based on what my fellow pals have shared earlier. Reiterating the objective shared by Kang, we introduced EGWO and compared with 5 different clustering algorithms. For intra-cluster distance, EGWO had the lowest mean and best fitness value. EGWO was significantly different from other algorithms based on the Wilkerson rank sum test. For convergence behavior, EGWO exhibited the strongest ability to explore and exploit, something which GWO failed to do so. Also, EGWO showed consistency in results with minimum degree of dispersion in box plot. Moving on, things got more interesting when EGWO was parallelized with MapReduce, benchmarked against 4 other parallelized algorithms on a large data set. EGWO once again emerged victorious with the highest F measure. Moreover, the best way to improve ourselves is to compare with ourselves. Therefore, as the author tried to increase the number of nodes for MREGWO, it caused a major speed up in results. It's definitely good for large-scale dataset as shown on the right. With all this, the true winner, the one and only, goes to EGWO. But wait, that's not the end. Every research unlocks new opportunities to improve existing ones. Hence, Spark could be introduced to reduce the computation time. Also, real-world datasets such as Twitter, video, satellite images can be utilized too. So, that is all from me. Once again, my name is Anik, along with Yingqiu, Kang, Ushani, and Kevin from Group 3, signing off.